Hey, how you doing? It's Mike here. In our last video, we discussed the uninhibited population growth model. And this was modeled by the differential equation dy dt equals k times t, which eventually, when solved, gave us the general solution of c equals to the kt power. And this was something that we've seen in prior courses, and I'm sure we've worked with in maybe some of our biology or anatomy and physiology courses. Maybe we've seen this if we've taken genetics. We've seen these populations grow. And this works well if we have a small population relative to the environment. And this key word here is relative. So if we think about a couple cells of bacteria on some agar plate, as they double, these 4 will become 8. I think I added too many. So they become 8. As these double, that 8 would become 16. And ultimately, we see that we would run into a restriction. We would run into a restriction because this small population would get too large. So then the uninhibited growth model will become an inhibited growth model. So the model changes because eventually these cells use up all the resources, they hit the max environmental space, so that uninhibited population growth model then will transform to an inhibited growth model. And that's the topic of this conversation and this video today, is how do we discuss what this growth model is. So let us assume that we have this function y equals to y of t, and this was not constrained by the environment. So this is the bacterial population when there's just a couple cells. It's not constrained by the environment. And this is a fair assumption as long as we said we have a small population. As long as we have a small population, because the effects of the environment become much more important as the population grows. So as the population gets larger, the effects of the environment will have an impact on how fast that population can grow. So first, let's go ahead and define some very important terms. Populations grow within their normal ecological ecosystems. I don't know if that's an oxymoron, but they grow within their systems, and they can only support a certain amount of individuals, whether or not these call these individuals cells or people or foxes or some bacterial population. We're gonna let the number L, so L can be anything, the number L be known as the carrying capacity. So the value L is going to be known as the carrying capacity. And this is going to be the number of things, I'm just going to call this things, that a certain ecosystem can sustain. So L is the carrying capacity. It's going to be the number of things, foxes, fish, I don't care, whatever it is. It's going to be the number of somethings that a certain system can contain. So going back to this model, y equals to some function of t, when this population is greater than L. So the population that we have is greater than the carrying capacity. The population, and maybe it helps if I write it in words, is greater than the carrying capacity. What do you think will happen when the population is greater than the carrying capacity? Then the population tends to drive toward L. So y starts approximating or gravitating to that value of L. Usually y is going to decrease. So we're going to see some of our population drop off. That's when the population exceeds the carrying capacity. But let's think of the alternative. And that is when y is less than the carrying capacity. So the population is less than the carrying capacity. So take a second and think to yourself and ask what's going to happen if the current population is less than the carrying capacity, what that natural equilibrium is what's supposed to be. You're going to see here that y will start increasing to a value of L. So y is going to tend to increase towards a value of L. And ultimately, they want to get to the point where y equals to L. We want to have that nice equilibrium, that relationship, and we're going to go one way or the other. And it tends never to be exactly equal. We'll go high, then low, and low, then high. But over a period of time, you're going to hopefully see this nice equilibrium develop. We can translate this into calculus. So translate into calculus. So the way that we notice that is that we're going to use this using the differential equation. And we're going to use a differential equation. But first of all, let's describe these relationships. So we know that the population must be greater than 0. We're not going to have a negative population. And our carrying capacity must be also greater than 0. It will never be equal to 0. It doesn't make any sense. So then we don't have a population with either one. So if dy over dt, the rate of change of the population with respect to time, if this is negative, so we're thinking the derivative of y is negative, this will occur if y, the current population, over the carrying capacity, one is larger than the other, the numerator is larger than the denominator. This will occur if y over L is greater than 1. Y over L is greater than 1. dy dt will be less than 0. The carrying capacity is greater than not carrying capacity, I said that backwards. So the population is greater than the carrying capacity. That's when we see dy dt being negative. And that means that the population will gravitate and become smaller such that it reaches the carrying capacity. Let's think about the opposite situation. What do we expect to see if the derivative of y with respect to time is positive, meaning that it's greater than 0? We know then that the population over the carrying capacity, the population is less. So we expect this to be less than 1. So here, the population is less than the carrying capacity. So we have these two circumstances. So this begs the other question I know most of you are probably thinking, what happens when the rate of change is equal to 0? I mean, there's no rate of change. So if dy over dt is equal to 0, we know this will occur at the most perfect relationship when the population is equal to the carrying capacity. So this is the mathematical translation of what we discussed earlier in terms of words. And we want to make sure that we feel very confident with this and we know how to recognize when these populations are increasing and decreasing, and that will help us substantially. So in calculus, in math, we always want to care about the extremes. I'm sure some of us remember in Calculus 1, we talked about limits at infinity and at negative infinity. We want to know what happens at these extremes. So let's think about when the population is far, 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 far less then the carrying capacity. Then the carrying capacity. Then the environmental constraints have little effect. So the environment has little to no effect. And that was like us in the petri dish, and we have 4 cells of bacteria. When the population is far less than that carrying capacity, the environment has little effect. So the growth rate here, the growth rate is a uninhibited model. So in this circumstance, that's when our model dy dt equals to kt kicks in. When the population is substantially less than the carrying capacity, we have this relationship. Mathematically, how do we represent that? We say that dy dt approximates kt, and this is if y over L approximates, think about this, the numerator is far less than the denominator. This approximates a value of 0. So we want to talk about a differential equation that meets all these requirements, that meets all these constraints. So without us dwelling into the production, I'm just going to go ahead and define a simple differential equation that allows us to model all requirements. And that's going to be dy over dt, and this will equal to some constant k times 1 minus y over L times y. So notice here we have this relationship of the population to that carrying capacity again. We know at the perfect scenario, the homogeneous scenario, we know y, not homogeneous, the equilibrium scenario, y equals to L, so we would get 1 minus 1, which would be 0. K times y times 0 gives us 0. So dy dt would be equal to 0. So that's how we can sort of work through this. So if y equals to L, if y equals to L, we know y over L is equal to 1. And this would imply that dy over dt is equal to k times 1 minus 1 times y. And this would be dy dt equals to 0. So that models extremely well. What happens if y is far less than L? That means 1 over L approximates 0. And this is when we get the relationship dy dt is equal to k times 1 minus 0, because remember this is approximating 0, all times y, and this is just equal to ky. And remember this is dy dt equals to ky, and this is the uninhibited growth model. So it's the uninhibited growth model. And let's think of the last circumstance, if y is far, far greater than L. If y is far, far greater than L. This is when we really don't have any model at all because we're going to get negative. Well, we do have a model, but it's negative. We're not going to worry about it in this circumstance just because this is a little bit beyond the scope of Calculus 2. But in totality, this relationship dy dt is equal to k times 1 minus the value of y over L all times y. This is known as the logistic differential equation. The logistic differential equation, which we just abbreviate by just calling it the logistic model. So this can be used in a lot of circumstances, but most specifically, we're looking at it in the relationship when y is far greater than L. So that's when we can really see what happens. And in that circumstance, if we think about this, if y is greater than L, then we know that y over L will be definitely greater than 1. If that happens, then dy over dt is equal to k times 1 minus some value that is greater than 1, one value that is some greater than 1, so I'm just going to call this 1 positive, times y. So here 1 minus some value of 1 that's positive will give us a negative constant times y. So here we would have a negative ky. And this is when that exponent ky becomes negative in that model, y equals e to the kt, but specifically this is e to the negative kt because we have a population that is decreasing in value. So this is how all these values are developed, all these equations are developed. It's all based off of differential equations, and I find them really exciting to work with.